So far, we've discussed mean and median as measures of center, but there are other helpful measurements that we can take, statistics that represent the center of a distribution. The first that we could talk about, which is actually very general, the mode of a distribution is the most frequently occurring value. And the reason why this one is helpful is because we can use this with both types of data, both categorical and quantitative. Here I have a sample data set. These are unleaded gas prices in the Sacramento area, taken from Gas Buddy. So these are in dollars. So a 3.15 represents $3.15 per gallon. And I have here 20 such data values. So these are quantitative, you could say continuous or discrete, but continuous is probably more appropriate. With continuous data, your mode is probably, you might not get a lot of recurring values. But in this case, we do, just because the way that gas prices are set. There are a few recurring or more frequent prices that show up. So if we're talking about in this data set, what is the mode? We have to look for the unique data value that occurs the most times. So if you go from, this is sorted, so I'm going from left to right, and then top to bottom, 319 occurs 3 times, so that's a contender. But then you look and 3.29 occurs 4 times, and that's the most frequent. So the mode here is actually 329. But again, mode isn't all that helpful if we're talking about quantitative data. But one thing that's really cool, though, is if you have one mode, then you have a unimodal distribution. And more than one mode, which is not defined here, we're just saying the most frequently occurring. If there is no mode, or if several data values occur most often, then it would be multimodal. So moving on, if we don't want to compute the mean or the median, we have a few alternatives. So for instance, the mid-range is a fast and easy alternative to the mean as long as the distribution isn't too skewed. So here's the idea. The mid-range is the sum of the first value and the last value, so x sub 1 and x sub 2, divided by 2. It's the arithmetic mean of just those two. You can imagine it as if we took the sample mean and instead of taking the sum of all those, taking the arithmetic mean of all the data values, we just pick the first one and the last one. So here, if we calculate this, we have 2.99 plus 3.39. It's already arranged for us, so that's nice. And if we take that mean, arithmetic mean, then we should get 3.19. Which is somewhere in the middle, so that works out. Just for the sake of checking that this is actually a good approximation, I'm going to calculate the actual mean, so the sample mean, which would be adding up all the data values and dividing by the number of dividing by the sample size. So remember, that would be x sub 1 plus x sub 2, ... all the way down to the last one, divided by n, and actually I get 3.2, or roughly 3.22. So that's not so far off. 3.19 and 3.22. Those are very similar. So this is a pretty good approximation. The mid-range, the advantages are it's faster, and in a pinch, easier to compute than a mean. On the other hand, if we are working with not the raw data set itself, but if we're working with a frequency distribution, we can approximate a mean from a frequency distribution. So an approximated mean if you want to find the mean from a frequency distribution, you would take the sum of your classes. So for each class, K is representing a class now, not the raw data itself. You're going to multiply the frequency of that class by the class midpoint. So really important, this is the class midpoint. And this is your frequency. And you divide that by the sum of the frequencies, which is the sample size. In the textbook, you'll notice that it says sum over K of the F of Ks, or F sub Ks, I should say. And that is equivalent to saying the sample size. They mean the same thing. So it's very similar, except instead of, because we don't have the raw data, right? Then we would have to approximate using the sample means. So going back to that example of the data, right? If we didn't have these data, but instead we had the classes, and the classes were of the form, so 2.90 to 2.99, 3.0 to 3.09. So our class width will be 0.10 or 10 cents, and we start at 2.90. So for the sake of exercise, why don't we illustrate how to do this? So we did this in the last chapter, but we should be comfortable working with it now again. And I think that's all the classes I'll need. Oops, there we go. Yeah, I shouldn't need more than that. So there should be 1 in the first class. So that's my first frequency. And then I've got 3 in the next class. So all the ones between 3.00 and 3.10. And then I've got 1, 2, 3, 4, 5. 5 in the next class. And then 1, 6, 6 in the next one. And then the last one I've got 5. All right. So 1, 3, 5, 6, 5. These are the frequencies. We need one more thing, though, here. We need to find the class midpoints. So the class midpoints, remember, we calculate each one by taking the arithmetic mean of the class limits. So the first one would be 2.90 plus 2.99 divided by 2. And that should be 2.945. A helpful hit when you're computing your class midpoints. They're all one class width apart, so you can just add 0.10 to each one. So this next one will be 3.045. The next one will be 145. Next one will be 3.245, and the last one is 3.345. Those are our midpoints, and so if we're computing the approximated mean, that's going to be the sum of the frequencies times the class midpoint. So these values multiplied by these values all added together. That will be 1 times 2.945 plus 3 times 3.045, and so on. Make sure you're aligning them correctly. The idea behind an approximated mean here, using it from a frequency distribution, is that really the important points are the midpoints. And what we're saying is each midpoint is an approximation of the actual data values, and we're multiplying that or weighting it according to how frequent values in that class are. And we divide that by the sample size, which is 20. Okay, so then if we take a minute to calculate that, 1 times 2.945, feel free to skip ahead a few seconds if you are not interested in hearing me or waiting for me to do the calculation. And I get 3.20. Exactly. So this is my approximated mean from the frequency distribution. And remember that my actual mean was 3.22. So that's actually not that bad again. This is a pretty good approximation. And the reason for this is that I chose a sufficiently small class width. If I had picked a larger class width, like going by 0.20 or even larger, this would have been a poorer approximation for the mean.